Hi everyone. Today I will present MPDiT, which stands for Multi-Patch Global to Local Transformer. This paper studies how to make diffusion transformers more efficient for flow matching and diffusion generation. The main idea is simple. Do not spend expensive high-resolution tokens in every transformer block. Instead, use larger patches early to model global structure, and use smaller patches later to refine local details. So the key message is, MPDiT keeps the strength of DiT, but delays expensive local computation until it matters most. Let me first explain the motivation. In latent ImageNet generation, the latent representation is typically a 32 by 32 grid. A standard DiT with patch size 2 converts this grid into 256 tokens. The problem is that every transformer block processes all 256 tokens. This is expensive, especially because attention cost grows roughly with the square of the token count. But not every block needs full local detail. Early blocks mostly decide coarse layout, object identity, and global composition. So the paper asks a natural question. Can we use cheap global tokens first and save the expensive local tokens for the end? This slide shows the architecture overview. MPDiT uses a global to local transformer design. It starts with patch size 4. That means the image is represented with only 64 tokens instead of 256. Most transformer blocks run at this coarse resolution. Then, an upsampling module converts the representation from 64 tokens to 256 tokens. At that point, the model also adds a fine patch embedding skip connection from the original input. Finally, the last few transformer blocks operate with patch size 2 and refine local details. So the model first builds a global image plan, then switches to local refinement. Now let us look more closely at the core design. MPDiT has two stages. In the first stage, it uses large patches with p equal 4. This produces a compact token sequence, so attention is much cheaper. In the second stage, it uses small patches with p equal 2. This gives the model access to fine spatial detail near the end of the network. For the default setting, most blocks are global blocks, and only k equals 6 blocks are local blocks. Importantly, the training objective does not change. The model still uses the standard flow matching objective. So the efficiency improvement comes mainly from the architecture, not from changing the loss. MPDiT also improves the conditioning design. The paper uses 3 conditioning components. First, shared 8in reduces repeated modulation parameters across blocks. Second, multi-token class embedding replaces a single class token with multiple class tokens. This gives image tokens richer class information. Third, FNO time embedding provides smoother time features for flow matching. The ablation table shows that these details matter. Multi-token class embedding improves FID from around 35 to 28.6. Then FNO time embedding improves it further to 24.5. After adding the MPDiT architecture, quality stays similar, while compute drops from 24.3 to 16.6 flops. Now we move to the main quantitative results. The important comparison is quality versus compute. At the B scale, MPDiT uses 16.6 flops and reaches FID 24.74. This is better than the selected efficient baselines at a similar compute level. At the XL scale, MPDiT XL uses 59.3 flops. This is about half the compute of the dense high-resolution SIT XL/2 model. With 80 epochs of training, MPDiT XL reaches FID 9.92. With 240 epochs, it improves to FID 7.36. And with classifier-free guidance, it reaches FID 2.05. So the result is not just lower compute. It is lower compute while keeping strong sample quality. This slide explains where the efficiency comes from. MPDiT does not simply make the transformer shallow. Instead, it keeps the same overall depth, but changes the token resolution used by different blocks. For MPDiT XL, the model still has 28 transformer blocks. However, 22 of those blocks operate on only 64 tokens. Only the final 6 blocks operate on 256 tokens. Because most computation happens in the coarse stage, the total flops are much lower. The GFLOP ratio is about 49.9% compared with the dense high-resolution model. So MPDiT keeps depth for representation power, but reduces token count for efficiency. Next, let us look at the ablation on K. Here, K means the number of local high-resolution transformer blocks. If K is too small, the model saves more computation, but does not have enough local refinement capacity. For example, K equal 4 is cheaper, but the FID gets worse. If K is too large, quality can improve slightly, but the compute savings become weaker. The paper finds that K equals 6 is a good efficiency quality sweet spot. For MPDiT-B, K equals 6 gives FID 24.74 at 16.6 flops. For MPDiT XL, K equals 6 gives FID 9.92 at 59.3 flops. This supports the main design choice. Use many cheap global blocks, then a small number of local blocks. This slide shows qualitative samples. The images show that MPDiT can preserve coherent global structure. For example, objects are placed in reasonable positions, and the overall scene composition is consistent. At the same time, the samples still contain local texture and class-specific detail. This matches the architecture very well. The early coarse blocks build the global plan of the image. Then the late fine blocks recover details at higher token resolution. Of course, qualitative samples are not the main evidence by themselves, but they make the global to local design intuition easy to see. To conclude, MPDiT has 3 main takeaways. First, it changes DiT into a coarse to fine transformer. It uses patch size 4 for global modeling, then patch size 2 for local refinement. Second, it cuts computation because most blocks process only 64 tokens instead of 256. Third, the conditioning improvements, especially multi-token class embedding and FNO time embedding, make training stronger. The main limitation is that the experiments focus on ImageNet class conditional generation. So future work could test this global to local design on broader datasets, higher resolutions, and text-to-image generation. My final summary is, MPDiT keeps DiT quality by delaying expensive local tokens until they matter most. Thank you.